Hi class, this is Blair. As I mentioned in the last video, we were starting to run kind of long on examples, but I hope you guys appreciate these examples. Uh, Complex numbers seem to be, for some reason, a common confusion for a lot of students. So I do really want to reiterate that don't overcomplicate these. It really is just basic trigonometry. It really all boils back down to just drawing a triangle. The only thing that you're doing differently is that you are labeling your x-axis with an RE for real numbers, and then you're labeling your y-axis with an IM for imaginary numbers. Okay, and you just have a new coordinate system and you're plotting the points a little bit differently. Okay, but either way, with this final video for the week, we are going to finalize our talk with finding roots of complex numbers. Okay, so with this root talk, we are going to talk about these two complex numbers, W and V, that we talked about in the previous video. So I'm going to copy those down and bring those down here. Okay, and I'm hoping you guys slightly notice that V, and I'm also going to make this realization that W, because we've already converted this to polar coordinates. So what did that end up being again? It was 6 CIS of negative pi fourths. Okay. Alrighty. Now let's start with this V. Okay, because I'm hoping you guys are making the connection to the lecture notes where we kind of talked about these principal roots of square root of 16 and the cube root of 8. And we came to a conclusion that the square root of 16 had two principal roots, plus or minus 4, but we just kind of left it at that. So let's pick this back up and talk about it again. So when we're taking the square root of 16, we made this conclusion that we get plus or minus 4. And all this means is that plus 4 squared, so if we were to reverse the process, that's going to give us 16, as well as negative 4 squared will also give us 16. Okay, so that's what we can conclude from this. But how are these our two only roots and they just so happen to be our principal roots as well? Well, let's kind of double check this, okay? So we can convert or model 16 as a complex number, just like we did above. So we said V is equal to 16. And if we were to convert this into polar coordinates, which we already did above and also in the previous lecture, and it's very simple, it's just 16 CIS of 0, then we know that this is the modulus of V, and we know that this is the angle, or our argument, right? Actually, let's not write out the entire thing. It's the lowercase a argument of V. Oh, it's also our principal argument of V because we chose a good one. We could have had that be 50 pi, and it still would have been a valid polar representation to this complex number. The only thing is that the alpha wouldn't have been our principal argument. We just so happened to choose our principal argument. Okay. But either way, if we wanted to find our roots using those W sub k's, what we're essentially doing is we're going to take, and notice another thing that we can identify from this is that this is the n that we're looking for. So we're looking for the nth roots, so that's going to be 2 roots. So we're looking for n is equal to 2. So we're going to take the square root, we're plugging that into here. Let's actually just rewrite what this W sub k is. So the W sub k is going to be the kth root of our modulus of our complex number z times CIS of some angle or some argument divided by n plus 2 pi k divided by n. Okay. So now what we're going to be plugging in is we're just plugging in these different k's. Okay. Oh, and this is actually should be a n. So I'm sorry about that. So we can get our closed representation or a closed form of this. So we can plug in a 2 for our n. We can plug in, again, this is just some modulus, but for our specific problem, it's a modulus of v. And so that's going to be 16. Then we're going to take the CIS of our initial angle, which is going to be 0. We're just calling that alpha, right? Divided by 2 plus 2k pi or 2 pi k, it doesn't really matter the order, divided by 2. Okay. Now, if we were to simplify this even further, square root of 16 is going to give us 4. CIS of 0 plus 2 divided by 2 is going to simplify down to k pi, or pi k. Okay. Now we can just simply plug in for k. So we're looking for 2 roots, so our 0th root, or our first root, is w sub 0, is going to be when k is equal to 0. So we're going to have 4 CIS of 0 plus pi times 0, which is going to give us 0. Okay, and in Cartesian coordinates, this is equal to 4. W sub 1, we're going to take 4 CIS of 0 plus pi times 1, right? Because now we're plugging in a 1 is 1 for k. So we're going to take 0 plus pi. Okay. So this ends up being 4 CIS of pi. Now we ask ourselves, what is this in Cartesian coordinates? We don't really need to actually go through the conversion. We should be able to see what this is in Cartesian coordinates. So let's sketch that out. So this is our real axis, this is our imaginary axis. We can draw an M better, okay? Well, we extend out by 4, and then we rotate around by pi. So that this would be our W sub 1. And notice that this is our W sub 0, right? And this W sub 1 is just going to be, so we went to the 4 in the real direction, positive 4 in the real direction, and we could have went to the negative 4 in the real direction, which is just going to be our Cartesian form of this number, okay? Which is in fact our 2 principal roots, right? We found 4, and we found negative 4 to be our 2 square roots of complex number 16, which just so happens to be those principal roots, okay, which we already knew from talking about it beforehand. Okay. Now, let's do one more example where we're not talking about a complex number that looks like a real number because it is a real number. Let's talk about W. Okay, so let's copy this stuff down again so that I don't have to keep on scrolling up to look at it. And let's make it all the same color. Okay, so what we're going to be looking for is what is W's third roots. So in other words, we're just looking for the third root of W. Okay, and we're trying to find all 3 possibilities of those. Okay, we've already converted this into polar coordinates, so we can just simply start plugging it in. Okay, so let's first get our W sub k, and this is actually an awful notation. So let's change this W to a Z. I'm going to hurry and go through and change all of these W's to Z's real quick. So we have Z, Z, Z. We're looking for all of our Z's third roots, which is the same thing as the third root of Z. Okay. So then we can say our W sub k roots are the nth root of our modulus of Z times CIS of our argument over our n plus 2k pi divided by n. Okay, now we just have one last thing that we need to do, is we need to identify that our n is equal to this 3. So because we're looking for 3 roots, okay, the cube root. Okay, so now let's kind of color coordinate this one so that hopefully it really sticks in for you guys, that really this is all that you're doing, if I don't jump ahead. So when we plug in the k is equal to 0, maybe if I don't get a little bit too premature because we actually haven't even plugged anything into here, right? So we're going to take the cube root of our modulus, which is going to be 6 times CIS of negative pi force divided by 3 plus 2k pi divided by 3. And once again, let's move this down. Now we don't need to know the cube root of 6. We can keep that as is. We just know that this is just some number. If we were to plug it into a calculator, we're just going to get some decimal. So we can just keep it as is. Okay. So we can say we have the cube root of 6 times CIS, negative pi force divided by 3 ends up giving us negative pi 12ths. And then we'd have plus 2k pi thirds. Okay. Now we can start plugging in our k's, okay, because this is the expression that we're looking at, okay? So k is equal to 0. We're just going to be plugging in for these k's right here. So k is equal to 0 is going to be, we're going to be plugging in for this k as well. W sub 0, that's just the label, right, is going to be the third root of 6 times CIS of negative pi 12ths plus 0. Okay, so our 0th root is just that cube root of 6 times CIS of negative pi 12ths. That would be our 0th root. For k is equal to 1, we're now just plugging in a 1 for this k expression. So w sub 1 being our label, we're going to have the cube root of 6 still, and that's something very important to notice, that cube root of 6 doesn't change, so we still have the same radii, or the same modulus, all the way around for all of these roots. So we're going to have cube root of 6 times CIS of negative pi 12ths plus 2 pi thirds, right? Because 2 times 1 times pi gives us 2 pi in the numerator divided by 3. Okay, now we need to be able to simplify this guy, so we can say that this is cube root of 6 CIS of, we want a common denominator, so we're going to have negative pi 12ths plus 8 pi 12ths. And so we are going to end up with cube root of 6 CIS of 7 pi 12ths. Okay, and for our last one, k is equal to 2. So we're plugging in a 2 for all of our iterations of k. So we're going to have w sub 2 for our label. We're going to have cube root of 6 times CIS of negative pi 12ths plus 2 times 2 times pi is going to give us 4 pi over 3. Then when we get a common denominator, we have cube root of 6 CIS of negative pi 12ths plus 16, right? 4 times 4, I lose my mind, no, that's 16, 16 pi 12ths. And this ends up being equal to the cube root of 6 times CIS of 15 pi 12ths. Which we notice that 15 pi 12ths can end up simplifying down. We could simplify this fraction down to, let's see, we could divide the top and the bottom by 3 so that we could get 5 pi fourths. Yep. But there's really no reason to do that. Okay. So now what I want to do is I want to make you guys have a realization of what actually happened here before we end this video. So we have our real and our imaginary axis. Okay, and let's see, where is our complex number z is going to be 6 negative pi fourths. So modulus is 6 and down pi fourths. So we're down right here at negative pi fourths. And this is our complex number z. Okay. Now let's make a slight realization. I'm actually going to erase, this negative pi fourths so it doesn't get in our way. I'm going to give you guys a realization of like what's happening with these roots. So we took a cube root of 6 and we rotated it down by pi 12ths. And so we just took this small little sliver and rotated it down. And we said that this is w sub 0. Okay. Now, for this other one, we took this other small little sliver and it's just slightly past pi halves. And that's w sub 1. Okay. Now this last one, it still has the same length, but it's at this 5 pi fourths. That's going to be w sub 2. And what we notice is the angle from here to here is equivalent to the angle from here to here, which is equivalent from the angle from here to here. Okay, so they're all equidistant in terms of angular rotation from one another, and they all have the same length. Okay, and that's how they relate to one another. And then they end up just having the exact same root. So they all have an equivalent, or not an equivalent root. They all have this property. So kind of like how, I'm going to scroll up real quick, don't hate me. If we were to take the square root of 16 gives us plus or minus 4, and if we were to revert our process and say plus 4 squared gives us 16 as well as negative 4 squared gives us 16. If you were to take w sub 0 and cube it, you're going to end up with z. And if you were to take w sub 1 and cube it, you'll end up with z. If you were to take w sub 2 and cube it, you'll end up with z. And that's the property that they share with each other, so they can revert that similar process. So either way, that's it for this week. Once again, I hope I really drilled this home with you guys. Do not overcomplicate complex numbers. If it's starting to look a little bit hairy to you, just draw it out in a complex plane and draw out your triangle, and you'll start to notice things will start to fall into place. Okay, so have a good week. Good luck with homework and quizzes. I look forward to seeing you guys in office hours. Bye.